Howdy! The purpose of today's short video is to introduce you to the Squeeze Theorem, which is a useful tool, but a fairly exotic tool, as we shall see. The spirit of the Squeeze Theorem is that we have some function f of x, and we would like to find the limit as f of x goes to c. And the way in which we use the Squeeze Theorem is to find two bounding functions. One of them will be h of x, and h of x is guaranteed to be above f. We find h of x so that it is guaranteed above f. And the other will be g of x, and we find a g of x so that g of x is guaranteed to be below f as well. And so this is our first condition in the Squeeze Theorem. If f is trapped between g and h, and now we have a second condition on our bounding functions, and that is that we have chosen h and g such that the limit as x goes to c of h and the limit as x goes to c of g are both equal to L. If these two conditions are met, that f is trapped between the two, and that h and g both go to L at c, then we are guaranteed that the limit as x goes to c of f must be L also. The intuitive reason for this is simply that h is always trapped between h and g, so that if h and g both go to L at c, then f is squeezed between the two and must go to L as well. Now, the proof is relatively straightforward. Choose an epsilon greater than 0. And now, because the limit as x goes to c of g is equal to L, and the limit as x goes to c of h is equal to L, we can find a delta greater than 0 such that when x is in the deleted delta neighborhood of c, then both g and h are in the epsilon neighborhood of L. Now I'd like to examine what these inequalities are saying geometrically. What they're saying is that g of x is in the neighborhood defined by L minus e to L plus e. And likewise, h of x is in the neighborhood defined by L minus e to L plus e. And so now this allows us to set up a glorious chain of inequalities. L minus e is definitely less than g, which is less than or equal to f by hypothesis, which is less than or equal to h by hypothesis, which is less than L plus e. And therefore, you'll notice that we have trapped f between L minus e and L plus e. And if I rewrite this statement as a neighborhood statement with an inequality, we can say that the absolute value of f of x minus L is less than e, which is exactly what we need for our limit. We have found a delta so that when x is in the delta neighborhood of c, f of x is in the epsilon neighborhood of L, and we are done. Well, okay, so that's the Squeeze Theorem. How do we use it? Really, the way in which we use the Squeeze Theorem is we find our bounding functions, f, g and h, that meet the two conditions required by the theorem. G has to be below F, and H has to be above it, and G and H both have to go to the same limit as x goes to C. And once we do that, we simply apply the squeeze theorem. Now, beginning students are often given those bounding functions, so using the squeeze theorem is just a simple matter of doing it. So, for example, here's a sample problem. If f is trapped between 4 minus x squared and 4 plus x squared, find the limit as x goes to 0 of f of x. So we see this set of inequalities, and just on a hunch we say maybe the squeeze theorem might apply here. And to do that, we see that we've already met the first condition. Now we just need to check the second condition. And lo and behold, when we check that second condition, the limit as x goes to 0 of both 4 minus x squared and 4 plus x squared are both 4. And therefore, we conclude that the limit as x goes to 0 of f of x is equal to 4 also. Sometimes we have to create our own bounding functions. And for that, we often appeal to the notion of range. For example, find the limit as x goes to 0 of x squared cosine 1 over x. This is an interesting problem because our limit rules do not apply to this function here. We have no guarantee that the limit as x goes to 0 of cosine 1 over x is anything. In fact, it's not. So we consider maybe we could use the squeeze theorem. A quick check on the graphing calculator. You can do this for yourself. Suggests that the limit should be 0. But a graph is not a proof, and so we now need to prove it. And so we're going to look for two bounding functions that trap this function and both go to 0. And what we observe is that the cosine of anything is always between -1 and 1. And so this suggests, in fact, it demonstrates that x squared times the cosine of 1 over x will always be trapped between -x squared and x squared. Notice that this only works because x squared is non-negative. And therefore, I don't have to flip the inequalities when I multiply through by x squared. Well, armed with this, I observe also that the limit as x goes to 0 of -x squared is the same as the limit as x goes to 0 of x squared, which is equal to 0. And therefore, I can conclude that the limit as x goes to 0 of x squared cosine 1 over x must be equal to 0 also. The key thing that we needed in order to make this happen was the range of cosine. That was the key. Tomorrow, we shall use the squeeze theorem to find a very famous limit, the limit as theta goes to 0 of sine theta over theta. And to do that, we will need two bounding functions that we will talk about tomorrow. See you later.